just a couple of quick notes before we get going today. Number one, there is no lab tomorrow, okay? I think everybody knows that, but just wanted to remind you that there is no lab tomorrow. Labs will start next Thursday, and so you don't need to worry about tomorrow. Use that to do whatever you want, catch up on your other classes or whatever. The second note is that test number one is going to be planned for not this coming Monday, but the following Monday. So I just want to give you a heads up for that, and we'll talk a little bit more about that next week. I'm not sure what the format is going to be yet, whether it's going to be online or in person or whatever. I haven't figured out what I'm allowed to or supposed to do with all the new restrictions and stuff. So put that in your calendar, and we'll figure it out closer to the actual date. So that's still a week and a half away. The tests in this class are all basically half the class. So they're 20-25 minute tests. And so probably what I'll do is we'll have the test and still have maybe a mini 20-minute lecture or something like that. So if you have any questions about that, let me know. It's going to cover topic 1 and the first part of topic 2. I actually meant to say 1, 2 in the first part of topic 3, but you know what? I will clarify what is exactly on the test next week. So don't worry about that yet. All right, back to topic 2. I reorganized some of the content in this course. You can see I'm getting the topic numbers incorrect. We're actually in topic 2, and we were talking about Alberta's water resources. And so here are Alberta's water resources, and we were talking about watersheds, and specifically I was going to talk a little bit about the Athabasca Watershed, because that is where we are. We are in the Athabasca River Basin. So that term, by the way, I think I mentioned watershed and river basin, those terms are usually used interchangeably. So you may see there's an Athabasca Watershed Council, for example, and so they're referring to the Athabasca River Basin and so on. You take a look at this. This is some interesting data about the rivers in Alberta, is that about 87% of them are north flowing, meaning they're going ultimately to the Arctic Ocean, which is kind of interesting. And of course, we were victims of that problem in 2020 when we had the giant flood here, because of course, when the water is trying to flow north and it thaws off in the south and it's still frozen in the north, that can lead to flooding. And that's kind of a very basic understanding of what happened in 2020 when we had the giant flood. So I think I mentioned before that the Athabasca River starts in the Columbia ice field, and I was just going to look. It's not showing on this map really necessarily, but the Columbia ice fields are kind of right there. So they're in the Rocky Mountains, and what you have are all these glaciers all over the place. Here is one of the glaciers, and I think last day I showed you this this photograph here, and you can go on these tours of the glaciers, and they have these specially designed buses for the Glacier Tours and so on. I've never been on a Glacier Tour. I hear it's a lot of fun, but I have been to this this glacier. You can visit it. It's kind of halfway between Jasper and Banff on that highway there, and there's a nice place to stop. And the interesting thing is they have these markers that show you where the glacier used to be in different years. And so this particular glacier is actually shrinking and getting smaller. The other interesting thing to say about the Columbia ice fields is they actually supply, or at least they're the source of 3 major river systems. So those 3 major river systems are, we have already mentioned the Athabasca River, Athabasca, and that ultimately flows north. It goes into Lake Athabasca, which flows into, I think, the Mackenzie River, and that ultimately drains to the Arctic Ocean. But the Columbia ice fields also provide water for the North Saskatchewan River. I'm not going to spell out the whole word Saskatchewan. I'll just use the abbreviation. And that is the one that goes basically through Edmonton, is the North Saskatchewan River. And that ultimately goes out through and ends up in Hudson's Bay. So depending on who you are, some people say that's the Arctic Ocean, some people say it's the Atlantic Ocean, maybe the North Atlantic Ocean. I'm not sure how to classify that. And the third one is the Columbia River. I think the Columbia River, or is it the Fraser River? I can't, oh boy, just going off memory here. And that goes to the Pacific Ocean, goes through British Columbia. So kind of interesting that these ice fields actually drain out to basically 3 different oceans. Really, really quite incredible. I wanted to show you this photo here. This is a photo I took, and this was just one of these days where I don't know what happened. I didn't even take it in black and white. Just the sun hit my angle, and I thought it kind of turned out really cool. I was on a little hike, and actually I believe this here is the highway, and the glacier you can see is right here. There's actually a parking lot down there, and you can hike up to see the edge of the glacier. So if you ever get a chance to do that, I encourage you to do so. It's really really quite stunning area, and very nice to see and cool to see the glaciers. And there's really actually a lot to see along that highway. It's really, really amazing. So there's the Athabasca River Basin kind of in one little graphic, and you can see all of the communities that the Athabasca River is basically providing water for. So Jasper, of course, is in the Park Jasper. Hinton is just outside of it. And you may recognize some of these other places, Whitecourt and Westlock and so on, and Athabasca, the town, of course, as well, and then Fort McMurray. And we have Fort McKay up there that is downstream from us, and Fort Chipewyan, which is downstream from Fort McKay. And well, actually, Fort Chipewyan is on Lake Athabasca, of which the river runs into. So it's obviously a very important river system for many of us living in Alberta, and drains quite a bit of water is provided to all these cities, and of course to any of the industries that are along there, such as the oil sands, which we're going to talk about at some point here this semester. Just some pictures. I like pictures of rivers, and just some pictures of the Athabasca River. Share them with you. I was looking for some nice ones, and you can see it's very nice to look at. Of course, rainbows. We love rainbows. Okay, so who uses the water? If you go back to that stat there, we'll talk a little bit more about quantities later on, but this is actually a huge amount of water here, right? 160,000, that should be cubic kilometers, and I'll need to fix that note, cubic kilometers of water. And so who's using all this water? And it turns out humans, I think the percentage is about 2%. So we're actually not really affecting the river very much, 2%. And who's using that river? Of course, we are, the public. And where are we? Municipal is right here. So municipal, if we're using 2% of the total water from the Athabasca, municipal systems are using 1% of that. So that's like 0.002%, very, very small. The big user is pretty obvious here, is the oil sands. They're using somewhere around 1.5%, if I remember correctly. And then we've got a little bit of agriculture, but not enough to be significant, 0%. There's other industries, of course, in northern Alberta and all over the place. So you can see the big user is the oil sands. The municipal is a small part, and these are some things we're going to talk about in kind of the second half of the course in terms of water usage and all those kind of things. But I just love looking at these stats because they're always very, very interesting. So what about Fort McMurray, or at least the regional municipality, in terms of our water sources? So Fort McMurray, I'm assuming all of you are living locally. We get our water from the Athabasca River, and so does Anzac. Not sure if anyone has been out to the town of Anzac. It's near Gregoire Lake, and it's right along the Athabasca River as well. Other communities in the municipality are Fort Chipewyan. I'm not sure why I have Fort Chipewyan twice. I probably meant to have Fort McKay up there. Fort McKay is also in the Athabasca River. Fort Chipewyan is on Lake Athabasca up there. And Janvier and Conklin are on Christina Lake, and they're kind of further down Highway 881 if anyone's been down that direction. So Fort McMurray, 5 rivers. Can you guys name all the rivers in Fort McMurray? Throw them into the chat if you know what the river names are around here. And you don't get any points for saying Athabasca, so because we said that one already, and it's actually labeled on the map. So what other rivers are here? Clearwater. All right. What else? Someone give me one more. Horace River. Okay, very good. So let's take a look at this. I actually have them on the map here. So the Athabasca River is the big one there. And so that's the one we see whenever you drive over the big bridge. And the Horace River drains into it. And if you take a look, there's Abasand here. And there's actually a few different access points. If you go hiking kind of behind Abasand, you can kind of climb down to the Horace River, and you can see it joins the Athabasca upstream of the bridge. And the Hanging Stone River is it actually goes by. It's not shown on here very well, but Grayling Terrace is that little neighborhood that's kind of found just across from the fire station there. And that one actually flooded back in 2013 or something like that. And the other big one is the Clearwater River, and that is actually what flooded in 2020. This is the one that goes along. I'm trying to think of where to describe that, but it's the one that's closest to the college, of course. You can see the Hanging Stone actually drains into the Clearwater. And the other one is this little guy here, the Snai, and the Snai is kind of just an offshoot there of the Clearwater River. And you can go down to the Snai in the summer, and there's all sorts of people on paddle boards and doing other recreational things like kayaking and canoeing on the Snai because it's nice and calm and still. And that's you can see it's kind of going along the golf course there at McDonald Island. So lots of rivers around here. I always thought that was interesting moving to Fort McMurray. When that was the first thing I read about Fort McMurray when I moved here, is it had 5 rivers. I was like, wow, that's kind of cool. 2 things to point out. And again, I'm not sure if this is going to happen or not, but I'm hoping that we can set up our field trips to the 2 drinking water treatment plants in town. A is the drinking water plant, and that's kind of what you see when you go across the bridge is the municipal area. It's not just the drinking water treatment area. There's other municipal offices and departments there, and that's kind of what you see when you go over the bridge. And the wastewater treatment plant is a little bit more downstream, and if you take a look, it's kind of after the this is the overpass that you would take to get up to Timberley, and it's sort of visible from the highway there. If you keep on going, driving north, it's a big blue building, and the yards are right there. So hopefully we can do both, or hopefully maybe even just one of these field trips. But we'll certainly know when we get to March, and if that's the case. So another thing that's worth kind of talking about with water management is talking about these things that we call green and white zones. And this has a lot to do with kind of management and legislations around how resources in these zones can be used, right? Sometimes people talk about the national parks as being 3rd category because they have their own legislations, but usually national parks, we're not taking resources from them. Like you're not usually logging them or taking water from them or whatnot, other than the small communities that live there. So what are these 2 things, right? The green is kind of unsettled land of the province. Often it's called crown land, but in terms of the legal definitions, those two things are not exactly the same thing, but generally we're talking about undeveloped, unsettled parts. And this is about 60% of Alberta and much of northern Alberta, right? And we're talking about northern Alberta, as we talked about last day, lots of lakes and rivers and wetlands and those kind of things. And of course, there's lots of resource exploitation there, forestry, oil, all sorts of things going on. And it's the provincial government that usually sets most of the rules and legislations and regulations, and it's them who you go through and need permits to do any resource exploitation. The white zones are settled, so we're talking about usually urban areas, things owned by townships and cities and municipalities and those kind of things. And this is kind of the other 40% of Alberta, as you can see there on that. And kind of the big difference is in terms of who can regulate things. Obviously, the province does have authority in some areas. You know, if you're discharging wastewater to a river and things like that, that is mandated by the province. But municipalities also have a lot of say in how things are done, kind of because it's their land, it's private land, right? So just some definitions there. And I'm not sure if you talk about these in your other courses, but I would not be surprised if that's something that you talk about when you get into environmental law and things like that. Kind of just to finish off this topic is who is responsible for our water. There is a Canadian Water Act. Generally, most of the provinces have their own water acts. So this is legislation and laws around water use, and they base them all off the Canada Water Act. And I think that actually those started to be introduced in the 1960s. I'm not entirely sure. But generally what happens is the province would grant licenses to any major water users. So that would be the city or the municipality, and any large industries that are taking water on their own. Such as the oil sands companies are going to also get water licenses from the government of Alberta, so the provincial government. All right, so just to finish off this topic, most topics I have some study questions along with them. I forgot to include them with topic 1. So here they are here. Here's the ones for topic 2. Sometimes I'll provide it as separate documents. So topic 3, for example, water chemistry, I'm going to actually have a full document of, and a lot of it is actually problem-based type of questions. So sample calculations and things like that you can work through when you're studying. So I encourage you when you're studying to work through these study questions. They're kind of what I've done is I've gone through and kind of decided what I think are kind of the big points. And so hopefully these will help you in your studying. All right, so that is topic 1 and 2. And like I said, I've done a little bit of reorganizing. I'm hoping it's going to make it for a little bit of a better course. So now we're going to start to get into some of the nitty-gritty stuff. And this unit here, topic 3, is maybe the most complex one, which is kind of one of the main reasons why Chem 101 is the prerequisite. But if you've done decently in high school chemistry, it's probably not a big deal. This is not going to be nearly as crazy as Chemistry 101. In fact, some of it should be review for you. And so there will be some new concepts as well. So some of the things I'm going to be kind of reviewing, and other things we'll be adding in some new concepts, particularly around water chemistry in general. So I really just wanted to introduce this topic today and talk a little bit about some parameters around water concentration. But before we get into this, I wanted to play this video for you. So let me just open up this link and I'll pull up this video. Probably going to have to do a new share. There we go. Hopefully there's not an advertisement. I bet you there will be. So I'm just going to play this video for you, and you can see they're talking about, bottled versus tapped versus filtered water in your house. So I'll just play this for you right now.
I tested Brita water, tap water, and a bottled water for anionic content, which basically means chlorides, nitrates, and sulfates, as well as for total organic carbons. Total organic carbons basically means everything except for inorganic carbons like carbonates in water, and as well I've tested for lead content in the water samples, each one. First of all, I was not surprised to find that the Brita water and the tap water had very little to no difference between them with respect to all characteristics, both with total organic carbon, which basically means it doesn't really remove anything, and with respect to chlorides, nitrates, and sulfates, I did not see any difference between the samples. When I ran the test with the Brita water and the tap water, I noticed that the samples, the Brita water was slightly lower, but statistically speaking, it wasn't enough for me to say that that the Brita water actually removed the total organic carbon content. I found that the bottled water with respect to nitrate concentration was 5 times higher than tap water, and the sulfate about maybe 7 times higher than the tap water. We looked at both tap water, Brita water, bottled water, and luckily none of them showed any lead content in them. I drink tap water. I drink tap water because I guess I've seen it so before, and I've had my students run some samples, so I'm pretty safe with it. I do let the water run. In Toronto and the outlying GTA area, we've always had a consistent level of water, good water, so it's safe, but we do test our water. I know they test it regularly. You have a population of about 5 million in this GTA. It's a vital and paramount concern that the water has to be tested, and I'm sure it's tested on a daily basis. So I don't drink bottled water. Yahoo!
Okay, so I thought that was a nice little introduction to water analysis. This is one of these things that I'm just amazed to hear the amount of misinformation around what's in your water. People don't trust tap water. I know somebody who doesn't trust bottled water. The reality is tap water is actually more highly regulated and tested than bottled water. And in fact, a lot of bottled water companies are basically taking it from the tap. They're basically taking tap water and they're putting it through some filters and bubbling out the chlorine, and that's often what is done. So it's something to think about. We are in the lab going to be testing tap water as part of our experiments, and we'll be learning a lot about what's in it. And the answer is it's actually really good. Now, not to say there are some circumstances where there have been municipalities that have had issues, and that's something that does happen once in a while. But for the most part, like I said, it's actually more highly regulated than bottled water, in fact, because it has to be tested daily for quite a number of parameters. So let's talk about some water chemistry here. These are kind of the topics we're going to look at. And what I want to do today is talk a little bit about ions and units of concentration, and I'm hoping most of it will be review for you. We are going to talk about water hardness and acidity and alkalinity, and that's where it gets a little bit more complex in terms of understanding which ions contribute to hardness versus alkalinity and things like that. But for the most part, it's actually quite straightforward. And so some of these things you're going to see on actually test 1 and test 2, because I want people to get a little bit of extra practice learning how to calculate these things. And we're going to kind of finish off the topic looking at gases and organics and other water quality parameters, and a lot of those things we'll see in some of the other units as well. And we're going to see a lot of these things in the lab as well. So there's a lot of kind of overlap between the labs and the lecture in this course. There are some references here. I'm also going to be putting up a couple of readings and a problem set that hopefully you'll find useful as well. All right, so firstly, some definitions, just some basic general chemistry, right? A solution is a mixture of something, and you can have liquid mixtures, like when we make juice. You can have solid mixtures like brass, for example, is a mixture of copper and zinc, I think. And so the solute is the stuff that is dissolved into the solution, and the solvent is the main medium. So we're going to be talking about water. So the solvent in this course is going to always be water. And it means that we're going to have a very predictable kind of chemistry in many cases. So what kind of things can dissolve in water? Many types of things. Pretty much anything that is polar or charged is usually water soluble. And this includes a bunch of things, right? Ions, we're going to really talk about ions for kind of 2/3 of this topic. And ions are going to contribute to things like their taste. So if you have too many dissolved salts, the water might taste salty. Not enough, it might taste flat. And that, of course, is going to contribute to its conductivity. We'll talk about conductivity in a bit here. And the types of ions may contribute to things like hardness or acidity or alkalinity. Sometimes we have dissolved gases or organic compounds or things that make the water look murky or turbid, and those are colloids. So today I want to talk a little bit about ions and a little bit about how we can kind of talk about concentration. So first question is, what is an ion? Anybody? How would you define an ion? So Ellen says it has a positive or negative charge. Basically, yeah, right? You've got it could be one element. You can see on this slide here, we have sodium, and sodium has a positive charge, so that's one element. Or it could be a complex ion, so you could have something like ammonia. Ammonia is NH4, and it also has a positive charge, and it has 1 nitrogen and 4 hydrogens. So something with a charge, and something with a charge will interact with water very readily, and of course, and will dissolve in water, just like it's shown on this diagram. We see the sodium. So what are some examples of ions that you think could be found in water? You guys could just put them into the chat, or you can say them. You can see I've got sodium there. I'm going to write some of them down here. Sodium. What are some other ones? Somebody has calcium. So this is kind of just a quick review of some important elements on your periodic table. We have, somebody mentions chloride. Fluoride. Okay, not all of these are as important to water quality, but that's okay. Chloride, not sulfate. So these are all good ones though for water quality. Sulfate is 2 negative, I believe. Magnesium. Good, so I think we're hitting on a lot of the important ones. I actually have a slide here showing a lot of the ones that we are going to be talking about this semester. So sodium, chloride, sulfate, magnesium, potassium, calcium, bicarbonate, carbonate, bromide, and so on. There's a couple here missing, but we'll get to them anyway. You can see this is showing some of the concentrations you might find in seawater versus fresh water. So hopefully you'll get familiar with the common ones, and if you're not so already, and you'll know, you'll be very easily be able to see the symbol and automatically know the element. Potassium is K, for example. That was not as intuitive as you might think. So notice this comment at the bottom of the screen. Oopsies, let me just go back to that. This comment at the bottom of the screen is sometimes these ions are called electrolytes, meaning that if you have them in water, the water has the ability to carry an electrical charge. So the more ions you have in a water, the better the water can conduct the electricity. So conductivity of water is something we can measure, and it's exactly correlated with the amount of total dissolved ions in that solution. And so that's a concept we're going to talk about over the next couple of weeks as we get into our water quality. So just an introduction now. Here's a few notes on some of the different ions and where they may come from. This is kind of Neil's area where, you know, I mean, he talks about different kinds of rocks and minerals and things that can contribute these particular ions to water, because of course water is raining and falling from the sky, and we'll pick these things up as it passes through the local geology. You can see that note about sodium. High sodium levels are often associated with pollution and different industrial processes, so that's something that people are looking for. A big one that you may see on here in a number of places is limestone, and we're going to be talking a little bit about limestone because it contributes to carbonate, bicarbonate. It also contributes to calcium and magnesium. I don't know if that was on the previous slide. It should be on there. We can add it. Limestone, particularly for calcium. And so that's a source of those things. And those things contribute to hard water and also alkaline water. But yeah, just a little bit of geology there for you. So we were talking about last week how water is a great solvent, and I just wanted to kind of, you know, show you a little bit of chemistry and how that works. So there's sodium chloride. Sodium chloride, you probably know, is an ionic structure. So you've got positive and negative charges, and it's actually a very strong structure. Sodium and chloride are pretty small elements, and they pack really tightly. But water can get in there. And what happens is water itself has these partial polar charges to it. So you can see a partial positive charge here on the hydrogens and a partial negative charge on the oxygens. And you have enough of those partial charges, and they can actually interact with the positive charges on the sodium and the negative charges on the chloride. And so water forms these little shells around those ions, and that's how they become, I guess you call it, as hydrated or solubilized. And so it turns out that sodium chloride and pretty much anything with a negative or a positive charge on it is actually very highly soluble in water due to this property. All these ions out there are very, very good at being dissolved by water. So these are the ones we're going to talk about the most, by the way. And I guess I'm missing phosphates on that list, which is actually down here. And all of them have different sources and whatnot, and different things in terms of health effects and whatnot, and we'll kind of get into some of those. Sometimes you see people who are worried about heavy metals such as lead or arsenic or things like that, and we'll certainly hint and talk about some of those things as well. So what I wanted to do today was just get into and start talking about units of concentration, because this is where we're going to have to do some calculations. And what I don't have with me is my calculator today, but we'll do a couple of sample calculations today. And I want to just kind of give you a little bit of a refresher and maybe introduce a couple of new concepts for today. So probably everybody here is familiar with molarity. Molarity is kind of the standard unit of concentration used in most chemistry courses, and molarity is defined as the number of moles divided by the volume. So the units are moles per liter, and sometimes we represent that as a large letter M, and we'll do a sample calculation of that in a moment. Something you may or may not have seen is a concentration called molality. So you can see it's similar to molarity, but not quite the same. It's actually moles of solute versus kilograms of solution. This is kind of an old school thing. I still see it once in a while with acids, and certain chemicals will come with the molality, but most people don't use it anymore. So we're not going to worry about it in this class. So don't worry about molality. Like I said, molality is kind of an old school thing that people don't really use anymore. Once in a while you might see it, so if you ever do, just look it up. We're not going to use it in this course. Something we will use a couple of times is percent, and you can talk about percent volume and percent mass. So the most common thing that is used is percent mass when we're talking about solutions that are made in water. So you might talk about a solution that's, let's say it's a 9% saline or 5% sucrose or something like that. And usually they're talking about percent mass. So on this page, two you really need to worry about are those two. And we'll show you some sample calculations here in a moment today. Another thing that is very, very important for water quality is understanding parts per million. Most ions, most things found naturally in water are not found in large concentrations. Maybe the ocean is an exception where the amount of salt in the ocean is massive. But if you think about water you're getting out of the river, it's 99.99% water. And so the things that dissolve in are very, very small amounts. And so it's more useful to talk about parts per million. And so part per million, by definition, is 1 milligram per liter. And so I'm going to assume that everybody knows that. Those are used interchangeably. You see sometimes in the same graph, you'll see parts per million and milligrams per liter used interchangeably. So just remember that conversion. 1 part per million is 1 milligram per liter, okay? And if you think about water, and again, this is something we're gonna start to get familiar with, is 1 liter of water, it turns out is 1 kilogram of water. So a part per million is also 1 milligram per kilogram of water. And if you make the units, if you convert a milligram to liters, that's a microliter, and you don't see microliter that often in the water quality industry. It's something that I think about a lot in the lab because I measure a lot of things in microliter quantities. But milligrams per liter is kind of the big one to remember there. Of course, some things are found in even smaller concentrations. There's parts per billion and there's parts per trillion. So parts per billion, so this is the conversion, is that basically 1,000 parts per billion equals 1 part per million. And parts per trillion is the same kind of conversion where 1,000 parts per trillion equals 1 part per billion. So I see parts per million and parts per billion the most, kind of just depending on what compound you're talking about. Parts per trillion is a really rare quantity to see, but I have seen it once in a while. And to make things even more confusing, once in a while with parts per trillion, I've seen PPT actually mean parts per thousand, which kind of just doesn't make it very fun. So don't worry about parts per trillion, but you do want to know parts per million and parts per billion. And the last one that we are going to get really familiar with, and probably no one has heard of, is called milliequivalence. And I'm not sure if I'll get a chance to really go into that today, but it's something that kind of has some usefulness with the chemistry of the whole thing. Milliequivalence, milli is the metric for 1/1000th. So it's a small volume or a small amount. And equivalence means you're trying to think about the chemistry in terms of the valence. If you think about calcium, calcium has a 2 charge to it. It's a 2 positive charge. So calcium is going to technically react twice when sodium would react once. And so that's what milliequivalence is trying to do, is think about the chemistry of that. And so milliequivalence is also kind of old school, but it's still used in water quality industry and in the toxicology and pharmacology industries. So it is important to know a little bit about milliequivalence. And it's also useful for us calculating out our water hardness or alkalinity. All right, let's take a look at a couple of sample calculations. And I'm hoping at least the ones we do today are not hard. I'm hoping that it's all review. If you do have problems remembering how to do these things, try the sample problems I'm going to post. And also come to me for help if you do have some problems with this. Like I said, this should be really straightforward kind of chemistry. So in this case here, we're looking at the molarity. Remember that the molarity is basically it's the number of moles of solute, right, divided by the total volume. Okay, so those are two things that we basically need to calculate. So first thing we're going to calculate is the number of moles of sodium chloride. So by the way, the little n means moles. So hopefully you know that. So in this case here, like I said, it's relatively straightforward type of calculation. We have 30 grams of sodium chloride, and we have the molecular weight right there, so 58.4. So this is the kind of thing, by the way, here, I'm just going to change my pen color for a second. And where is that? Ink color. So this is the kind of thing that I always like to do, because you can see if I put all my units, I can see which ones cancel out. So in that case, my grams cancel out. So my answer is not going to be in grams. The moles is on the bottom. So that means in the end, it's going to flip on the top. And so my final answer, crunch this into my calculator, is 0.51 moles. Okay, so that gives me the top part of my molarity. And reading the question further, it's a 500 milliliter solution. So of course, that is equal to 0.5 liters. So I'm hoping everybody can convert easily between milliliters and liters. It's 1,000 times difference. When we have milliliters, we divide by 1,000 to get to liters. When we have liters, we multiply by 1,000 to get to milliliters. So the concentration is just taking those two numbers, right? 0.51 moles divided by 0.5 liters. So notice I rigged the math to make this nice, easy math in this case here. So the answer is basically 1.03 moles per liter, or you could say 1.0 big M for moles per liter. Okay, so there's my answers. I know your next question is, people are probably wondering, oh no, what about significant figures? I have this to say about significant figures. I think they're important, yes. But I'm not going to be testing you on significant figures, okay? I'm going to be assuming that most people kind of have a basic understanding of them. And my rule of thumb is go for 2 or 3. Okay? So in that case there, technically this is correct. 2 past the decimal place is also almost correct. And I would accept that, not a problem. If you're going really bad with the significant figures, sometimes that will affect your result in the end. Particularly if you're rounding off early in these calculations, sometimes it can mess you up a little bit. But other than that, I wouldn't worry too much about significant figures. So if you have any questions about that, do come in and talk to me as well. So that gives us the answer to question A here. So what about question B? So question B says, would this be the same concentration if I added 30 grams of sodium chloride to 500 mils of water? And you can see down here in the bottom of my slides, I have my answers, okay? So if you're looking at these questions later, I encourage you to practice them all, and you can see if you get the same answers. And you can see the answer here is no. No, it is not the same. So read very carefully here. The top part is a 500 ml solution. The bottom part is actually about 530 mils, because 30 grams of sodium chloride is approximately 30 milliliters. And so in that case, you're not actually having a 500 ml solution, okay? So just something to think about, particularly once you start working in labs. This is something to consider when you're actually making solutions, because you need to know what the final volume is to calculate out a concentration. And so it matters how you measure this. So the correct way to make a solution, again, not something I'm going to test you on in this class, but a correct way to make the solution is you add, whatever needs to be put into it, so the sodium chloride or whatever, and then you add the solvent, the water, up into that volume, right? So you'd use a volumetric flask or something like that. So that's molarity. I'm hoping everybody knows how to do that kind of calculation. One more for you. This is kind of the opposite kind of calculation, where the first one asked me what the concentration was. This question here is asking you the opposite, asking you how many grams are required. Okay, so we've got the information here, we've got the molecular mass, we've got the volume, we have the concentration. Okay, so in this case here, we're also going to start off by trying to figure out the number of moles. And the number of moles is basically equal to the volume times the concentration. And those are things that we have there in the question, right? So we're going to convert this to liters. So that's 0.25 liters, okay? So 0.25 liters, and the concentration is 0.8 moles per liter. So if you take a look, notice that my liters do cancel out, okay? And I'm left with moles. So the number of moles is 0.25 times 0.8, which is 0.2. That one I can do in my head. And what do we ask for now is the number of grams. So this is just the conversion. So the mass is, of course, the number of moles times the molecular weight. So 0.2 moles times 120 grams per mole. So notice moles is going to cancel out with that. And the answer is 24 grams. Okay, so like I said, I'm hoping that is no surprise to anybody. Very standard kind of introductory chemistry stuff, and hopefully you've done that 1,000 times already, and you can do those type of calculations very easily. In the end, we're not going to use molarity a lot in water quality because this is very high concentrations. Most of the things we're working with are going to be parts per million or percentages and things like that. And so actually, I'm just looking at the time, and I guess that's where we're going to finish today. So next week, we'll come back, we're going to talk about percentages and parts per million and milliequivalence, and all of those, for water quality anyway, are much more important than molarity. And so we'll hopefully get really familiar with doing those type of calculations. All right, that's the end for today. So do not come to the lab tomorrow. Come back on Monday for Monday's lecture, and we'll pick it up there. So hopefully everyone has a wonderful week and a great weekend, and we'll see you on Monday.